Welcome back to the channel. Today we are starting with Applied Physics 2, where we will look at quantum mechanics. This will our part 1 for that, so let's get started. Quantum mechanics represents a revolutionary approach to understanding the physical world at atomic and subatomic scales. Unlike classical physics, this field challenges our traditional intuitions about how matter and energy behave. At its core, quantum mechanics introduces mind-bending concepts that fundamentally reshape our perception of reality. Key ideas like wave-particle duality, de Broglie waves, and the uncertainty principle demonstrate that the microscopic world operates in ways that defy our everyday experiences. By exploring these principles, we can unlock profound insights into the fundamental nature of matter and energy. Wave-particle duality is a fundamental concept in quantum mechanics that reveals the dual nature of particles like electrons and photons. In certain experimental setups, these particles can exhibit wave-like characteristics, such as interference and diffraction. For instance, when light passes through a double slit, it creates an interference pattern typical of waves. Simultaneously, light can also behave as discrete packets called photons, demonstrating particle-like properties. This duality highlights a crucial limitation of classical mechanics and underscores the need for a more comprehensive quantum mechanical framework to explain subatomic phenomena. Let's delve deeper into the particle nature of waves. Photons, which are light quanta, showcase fascinating particle-like properties. They can be localized and carry discrete amounts of energy, calculated by the equation E equals h nu, where h represents Planck's constant and nu is the frequency. This understanding reveals that energy is not continuous but comes in specific, quantized packets. The profound implication is that our classical understanding of physics breaks down at microscopic scales, necessitating a more nuanced quantum mechanical approach to comprehending the fundamental behavior of matter and energy. Louis de Broglie proposed a groundbreaking theory suggesting that all matter possesses wave-like properties. His fundamental equation lambda equals h/p relates a particle's wavelength to its momentum, where lambda represents the de Broglie wavelength, h is Planck's constant, and p is the particle's momentum. This theory dramatically expanded our understanding of wave-particle duality, proposing that not just light, but electrons, protons, and even larger objects have associated wavelengths. The Davison-Germer experiment and electron diffraction experiments provided crucial experimental validation, confirming de Broglie's revolutionary hypothesis about the wave nature of matter. The Davison-Germer experiment, conducted in 1927, was a pivotal moment in validating the wave nature of electrons. In this experiment, researchers directed a beam of electrons at a nickel crystal and detected the scattered electrons at various angles. Surprisingly, the scattered electrons produced a diffraction pattern reminiscent of wave interference. This observation was groundbreaking, as it demonstrated that electrons, previously understood as discrete particles, could exhibit wave-like behavior. The experiment conclusively supported de Broglie's hypothesis and provided empirical evidence for the wave-particle duality of matter. Electron diffraction provides further compelling evidence for the wave nature of particles. When an electron beam passes through a thin metal foil or crystalline structure, it generates distinctive diffraction patterns characteristic of waves. This phenomenon is not just a theoretical curiosity, but has profound practical applications. Scientists widely use electron diffraction techniques to study the intricate atomic structure of materials. By observing how electrons interact with crystal lattices, researchers can gain unprecedented insights into the microscopic world, revealing details about material composition and atomic arrangements that were previously invisible to classical observation methods. In quantum mechanics, the wave function psi is a fundamental concept that represents the complete state of a particle or quantum system. It's more than just a mathematical abstraction. It contains all the information about a quantum system. The probability interpretation is particularly fascinating. The square of the wave function's magnitude gives us the probability density of finding a particle in a specific position or state. This wave function has two critical properties. It must be continuous, meaning it changes smoothly, and it must be normalizable, ensuring that the total probability across all space equals exactly 1. This probabilistic nature challenges our classical understanding of deterministic physical systems. A wave packet is a superposition of many waves with different wavelengths and amplitudes, localized in space. This concept is essential in describing particles as it represents both their position and momentum due to the wave components. The formation of wave packets allows us to understand particle behavior in quantum mechanics. There are two key velocities associated with wave packets. Group velocity. This is the velocity of the overall wave packet and is associated with the particle's velocity. It is calculated by considering how the wave frequency changes with the wave number. Phase velocity. This is the velocity of a single wave within the wave packet. It is determined by dividing the wave frequency by the wave number. And from here you can understand what relationship the group velocity and the phase velocity have between them. Understanding these velocities helps in studying the dynamics of particles at the quantum level. The uncertainty principle, proposed by Werner Heisenberg, is a fundamental concept in quantum mechanics. It states that certain pairs of physical properties, such as position and momentum, cannot be measured simultaneously with perfect accuracy. Specifically, the more precisely one property is measured, the less precisely the other can be known. This principle is represented by the inequality. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a constant value, known as the reduced Planck's constant divided by 2. This principle challenges our classical understanding of measurement and underpins the inherent limitations of observing quantum systems. The principle can also be extended to energy and time, indicating that the product of the uncertainties in energy and time is always greater than or equal to a constant value, specifically the reduced Planck's constant divided by 2. This explains why virtual particles can exist for brief moments of time, even if they seemingly violate the conservation of energy. Understanding the uncertainty principle helps us grasp the fundamental limits of observation in the quantum realm, challenging our classical intuitions. Quantum mechanics isn't just a theoretical curiosity, it has profound real-world implications. Electron microscopes, based on de Broglie wave principles, allow us to resolve atomic-scale structures with unprecedented detail. Quantum computing leverages wave-particle duality and uncertainty principles to create revolutionary computational technologies. Numerous technological innovations, including semiconductors, lasers, and transistors, have emerged directly from quantum mechanical concepts. Beyond technology, quantum mechanics has a significant philosophical impact, challenging classical determinism by introducing a probabilistic understanding of physical systems. It reminds us that reality at its most fundamental level is far more complex and mysterious than our everyday experiences suggest. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.